Resonance in chemistry. You know, many of my students find the topic of resonance difficult. They get frustrated with it because they end up guessing some of the times when they're drawing structures and where to put the curly arrows, where to move the electrons, and so it can feel like they're guessing. And resonance is a topic that's really important. With a system, a simple system that you can follow, actually drawing resonance structures is quite straightforward, and that's why I've created this video to give you a simple system for drawing resonance structures in chemistry. So why must you understand resonance? Well, once you understand it, you don't have to guess anymore, and it stops any memorization of lots of chemical structures, because memorizing chemical structures is going to make it a lot harder. It's going to make it dull to learn, and you don't need to. You can actually work them out once you follow this simple system. The reason why we talk about resonance so much in chemistry is because it helps us to keep track of where the electrons are, and you know that it's the electrons in chemistry that are the important and the interesting part of a molecule, because it's the electrons that form bonds, it's the electrons that carry out reactions between different molecules. Now, the reason why we talk about resonance structures, it's similar to, take for example, the motorway around London in England, which is called the M25. Depending on the time of day or whether or not there's been an accident on the motorway, the traffic on this motorway will vary. So in the top picture we have free flowing traffic where we have multiple lanes and all the traffic can flow freely, and they do. Whereas in another picture of the same motorway, you get a build-up of traffic where it has a different look and a different distribution of traffic on the motorway, yet it's the same motorway. And that's exactly what it's like with resonance. We're looking at where the electrons are because they can move. Once they have multiple bonds, they can actually move through a system, and therefore where the electrons are in one case may be different when they have moved and you look at another case. So resonance is just a way of us keeping track of where the electrons are. Okay, so let's now have a look at the system for how to draw resonance structures. I've shown here an example where we have a molecule with various bonds, single bonds, double bonds, and it also has a negative charge. The first step in drawing resonance structures is to identify the charge or the lone pair of electrons in your molecule. So that's quite easy to do here. Here we have our charge indicated. The second is to identify the conjugation path. Now, what is conjugation? Conjugation is where you have alternate single, double, single, double, single, double. You need to have those alternating single, double bonds because it's the pi system from those multiple bonds that allows the electrons to undergo resonance and be distributed around the system. So in this case here, as shown in step 2, from the charge there's single bond, double bond, single bond, double bond. So that's our conjugation path. Now if you were to have a look at the anti-clockwise direction, you can see it's single bond, which is not conjugated. So there is only one conjugation path in this molecule. Now step 3 is where you push the electrons into the adjacent single bond. The arrow, that single arrow there, that curly arrow, indicates movement of 2 electrons. Notice that it is drawn pointing towards the center of that single bond to indicate movement of 2 electrons directly into that single bond. Now step 4, this is where there are 2 choices that you have when drawing resonance structures. So I'll show both of them. Step 4.1 is from the double bond into the next single bond, or you can have Step 3, push the electrons into the adjacent single bond. From the double bond onto the adjacent atom. That's step 4.2. Look at where that arrow is pointing. It's pointing directly onto that carbon atom to show that the electrons will stop and they will be positioned directly on the atom. So they're the two paths that you have. I'm going to go through each of them now in detail to show what you do next, but you do have two choices. Okay, let's have a look at, we're going to have a look at where we stop on the atom. So, step 3, push the electrons onto the adjacent single bond. Step 4, from the double bond onto the adjacent atom. Once you stop at the atom, that's like the stop sign. That's when you draw out the resonance structure. Okay, how do you draw out the resonance structure? You first of all indicate the correct arrow. Remember, resonance is not a reaction. It's just the distribution of electrons, so you show the resonance arrow. Next thing, this is where you just draw what you see. You don't have to learn the structure off. This is where it stops this memorization of chemical structures. Follow the arrows, the curly arrows, because they will tell you where the electrons are to be found. So the atoms haven't moved, it's just the electrons. So the first arrow shows us movement of two electrons. So we now have a double bond where there was a single bond in the first structure. We still have the other double bond in the system, and we now have a negative charge. Those two electrons are sitting directly on the carbon atom as indicated by that arrow. Notice in the two structures we still have a negatively charged molecule because charge must be conserved in resonance. So we have to end up, if we started with a negative structure, we must end up with a negative structure. Okay, let's have a look at where we go from the double bond into the next single bond. So step 4, part 1. So step 3, push the electrons into the adjacent single bond. From the double bond into the next single bond. Sometimes this can create a loop depending on the length of your conjugation path. But in this case here, we're now going to go step 4.2, where we're going to go from the double bond onto the adjacent atom. So that's all the arrows drawn. Draw what you see, resonance arrow, show the atom, show the framework of your molecule, and the last stage, fill in where the electrons are. So our first arrow shows us we now have a double bond. Our second arrow indicates we now have a double bond as shown in this position. And our third arrow shows us we have a negative charge directly on that substituted carbon atom of the ring. Again, notice we still have a negatively charged structure because charge is conserved in resonance. Okay, let's have a look at another example, just again to reinforce how you use this system. First step, identify the lone pair of electrons. In this example here, this structure does not have a charge, but it's the lone pair of electrons on the nitrogen that will take part in resonance. Okay, first step, identify your conjugation path. So that's shown here. So from the electrons, we have a single bond, double, single, double, single, double, all the way around the ring. Now I'm going to draw out this structure here, this para-amino-benzoic acid. I'm going to draw it out showing the carboxylic acid functional group because this is a highly conjugated molecule that I've shown you as a deliberate example. It has more than one conjugation path. There is actually a second conjugation path which goes from the lone pair of electrons on the nitrogen right the way to the oxygen of that carbonyl group of the carboxylic acid. Okay, so let's have a go at drawing a resonance structure following our simple system. Step 3, from the electrons into the adjacent single bond. Now step 4, from the double bond into the adjacent single bond. From the double bond into the adjacent single bond. This is where the loop system comes in. And finally, to get to our stop sign, which is where we know we stop the resonance, is from the double bond onto that oxygen adjacent atom. So there is the whole resonance sequence with all of the arrows shown. Draw what you see, put in the resonance arrow, put in the atoms showing the framework, and finally put in your electrons. So the first arrow shows us we now have a double bond between the nitrogen and the ring. Second arrow is where we have movement of 2 electrons. We still have a second double bond in that ring system that hasn't taken part in resonance, so that still stays in that position. The third arrow indicates we now have a double bond between the carbonyl carbon and the ring. And finally, we now have a single bond between that carbon and oxygen, but we have a negative charge directly on the oxygen. Now, looking at this, we started off para-aminobenzoic acid is neutral. There is no charge. The structure we've drawn has a charge, but also remember nitrogen has 4 bonds, so there's a positive charge on the nitrogen. So overall, we have maintained charge. We have a neutral structure in our resonance structure because the positive charge and the negative charge cancel each other out. So that's showing one of the key resonance structures for this para-aminobenzoic acid. I'm going to show you again a second resonance structure where we actually stop at the adjacent atom. So again, lone pair of electrons, we know our conjugation path from the electrons into the adjacent single atom. From the double bond onto the adjacent atom, we're stopping at this point here because that arrow indicates we're stopping on the adjacent atom. Now draw what you see. So there's going to be a double bond between the nitrogen and the ring. The other double bonds in the ring, in the benzene ring, are still in the same position, so I'm putting them in first. Now I'm going to show the negative charge on that carbon atom that was indicated by the arrow where the electrons have stopped. And also remember we have a positive charge on the nitrogen. So overall, our resonance structure is neutral. Remember the steps for drawing resonance structures. Number 1, identify the lone pair of electrons or the charge in your molecule. Identify the conjugation path. Then push the electrons into the adjacent single bond. From the double bond into the next single bond and onto the adjacent atom, which is your stop sign. You may also have a loop depending if you've got multiple double single bonds, because you may go from the double bond into the next single bond, from the double bond into the next single bond, etc., etc. But then you will go and stop onto the adjacent atom. So that is the simple system for how to draw resonance structures.